Hello and welcome to this low-level JavaScript series on building parser combinators from scratch. This is the third episode in the series, and you can check out the rest of the episodes in a playlist which is linked below. In the previous episode, we began to implement the core mechanical parts of our parser combinator system. In this episode, we're going to see how we can wrap our system up in a class and how we can do some more useful things with it, like implementing a map method. Why would you want to do that? Well, in traditional methods of parsing, the process is broken up into a couple of different steps. So the first step is translating the stream of characters into a set of tokens. The second step is taking that set of tokens and matching them recursively against a grammar that you've defined. And eventually that yields a tree structure. But in parser combinators it's a little bit different because they're doing both things at the same time. And they have the added advantage through concepts like map to go back and reapply whatever kind of structure they like on the parse result. The parser library that we're going to be building in this series will later be used to write parsers for various projects, including one for an assembly language that we're going to design, and another for a C-like language that we'll eventually be writing a compiler for. Okay, so the core of what we've built so far revolves around these functions that take in a parser state and return a new parser state. That part isn't going to change at all. All we're going to do is place the function inside a class. So let's first create a class called parser. I'm going to do that under these functions here. We of course don't need to extend anything. We're going to have a constructor. And that's going to take in the parser state transformer function, which is a very fancy way of calling it. Parser state transformer function. Or maybe we'll just make that a tiny bit shorter. And we'll just apply that to this. So we keep it... And now that's quite simple. We haven't really done anything. We've just taken what we already had and given ourselves the ability to put it inside a class. The second thing we can actually do is to come and grab this run function that we've written down here and jam it inside as a method. So inside, previously we were taking a parser. Well, we don't need to do that anymore because now we have that here on this. So all we need to do is take the target string. And we can pretty much copy and paste everything out of here. So we build an initial state. And the only thing is that instead of running parser, we'll do this dot parser state transformer function. And then we'll save. And we should already be able to see if this works. We can delete this run function now. Let's come up here. Let's take our two parsers that we have and just wrap them in this class. So new parser. So when we supply our string to the str parser, what we're going to get back is a new parser. And that parser is going to contain our transformation function. We'll do the same thing with sequence of. We'll take the parsers, and then when we have this parser state function that we're going to use to transform, we'll just wrap it in a new parser. And then here is just how we use it. That's totally fine. So now we just need to change a couple of little things, because since we're passing parsers into sequence of, we need to come in and kind of correct the way that we're running the internal parser, because now what we have is this P is a parser, but it actually has a transformation function inside. So what we need to do is to grab this key and run on that instead. So we're running the parser state transformer function. That should be good. And string doesn't require it because we don't pass any parsers to string. This should now work, although it should lead to a parser error. Run is not defined. Console log. Oh yes, of course. Parser.run. Try that again. And great. So that kind of works the way we would expect it to. And what is this actually expecting? Because we can write that string. Hello there, goodbye there. All right, so we've actually rewritten the main system as it were now. We can actually wrap those in up into a class. But now we can start to do something more interesting, which is we can start to implement map. So just like array map needs to return a new array, parser.map needs to return a new parser. So we can just straight away return a new parser. And here we can take our parser state. We already have the main function that we're going to use. And we could essentially at this point just return update parser result. And here we have our next state. And what we want to do is just run the function on the old state. So next state.result. And right here, what we have is a parser that is able to parse with any normal methodology, but then to immediately apply a transformation to it. So let's try that out. Oh, of course, we need to return the new parser. We've managed to transform the structure here. And we could do something much more drastic, like return an object here instead. And that object could have a value, for instance. So here, we're able to take that structure and change it and modify it, but it's still a parser. Okay, but I want to modify the map function because I actually want to make a distinction between what happens when we map when there is an error and what happens when we map when there's not an error. If there's an error, I actually want map to basically have no effect and to not change anything. And so what we can do is we can add a condition here. So if the next state is an error, then let's just return the next state. Don't modify anything, and otherwise we'll update it. The reason I'm making this distinction is because I actually want to write a second method here called error map. An error map is just going to be exactly the same as map, but it's going to have this condition switched around. And what's going to happen is if this is not an error, we're going to return just the regular next state. But if it is an error, we're going to update the error. And we're going to do that in the same way. But I'm going to pass a little bit more information to this, this function. I'm also going to pass the index, for instance. This is quite useful because just as we can apply structure to our successful results, we could just as well now apply structure to our unsuccessful results. So we could also error map this. Oftentimes, the errors that are coming from the parser combinators are not going to be specific enough to your actual problem and that you want a user to use. And so you need a way to imply structure even on the errors. Okay, so the next thing I'd like to do is to implement some more useful parsers. So far, we've only implemented parsers that can capture predefined strings or sequences of strings. And that's not really that useful because if you know what you have to parse, then there's many other ways you could do it that are probably easier than this. So let's add a couple more parsers that allow us to capture more general data. By far, the most useful and general parsers that we could implement and will use are the letters and digits parsers, which match alphabet, characters, and numbers. Let's start with letters. Okay, we're going to base our implementation on the string parser. I'm going to call this letters, and we can get rid of this s argument. We just immediately return a parser. All the normal things will apply. We will destruct our parser state. We will check if we have an error. If we have an error, we will just hand it off down the chain. We will slice the target string to the current index. We will throw an end of input error if we get end of input. And all I'll do here is change the name of the function. And here we can get rid of this references to string s. Got unexpected end of inputs. So obviously we can't match a string directly like we're doing here. What we need to do instead is to use something like a regular expression to test if we have letters at the beginning. And that's very, very straightforward. So let's say the letters regex is going to be, we'll start from the beginning of the string, and we want to match the characters A to Z, also the small characters A to Z, and we want to get as many of those as possible. So this is our regular expression. Okay, and what we can do here is we can try to test our string against our regular expression. And the best way to do that is to create a match. Regex match is going to equal sliced target, which is a string. And strings have a built-in method called match. Match simply takes a regular expression, and our regular expression is our letters regex. And now, the nice thing about the return value of match is if it's successfully able to match something, it will return an array, and the first element of the array will be the thing it matched. If it's unable to match anything, it will simply return null. So all we have to do in the beginning here is to check, do we have anything in the match? If we have a regex match, we can update the parser state, and the index will be the regex match first element, and the length of that, and then the actual string will simply be the match itself. Now, of course, if we don't make it through here, that means that we weren't able to match any letters. And let's say error letters couldn't match letters at index. Simple. Okay, let's give that a try. So let's remove this other parser we have here, and we'll simply use letters. Error. Oh, of course, yes. We need to actually successfully get the match, not that we don't have a match. So let's try that again. Is error is false? We managed to match the string goodbye. But if we only had the string good, then we would also be able to match that, as well as the string hello, and many other kinds of string. And of course, if we had something that wasn't a letter in there, we would get an error. To match digits, so I'll copy all of this. I will change instances of the word letters to digits. And the only thing we need to change here is the regular expression. So we can come in here and simply say we expect to get the characters 0 to 9. We can try that out. And so here we were able to successfully capture these digits. We could use something like sequence of, and we could capture digits, then letters, then digits. We now have a generic way. We can fill this in with anything we like, 1D2, and that will match just the same as this is able to match. Okay, and so finally, the last thing I'd like to implement today is the parser combinator choice, which will illustrate as well why immutability is quite important in this parser combinator system. Just like sequence of, choice takes an array of parsers, and it tries to advance the parser state using each one of them. If any one of them succeeds, then that's the result that's returned. Otherwise, it just tries the next parser in the queue. If no parsers are able to succeed, then that's considered to be an error. We can copy the code of sequence of and begin there because it's quite similar. I'll rename to choice. We still take an array of parsers. We still propagate our errors. In this instance, we don't need a results array, and we actually don't need a temporary state. So what we're going to do is we're going to create a next state just within the loop through the parsers. So we'll check this next state, and we'll simply pass in parser state. And what we can do is we can check if we have an error. Well, if it's an error, we actually just want to go to the beginning of the loop again. So what we really want to do is we want to check if it's not an error. And if it's not an error, that's great. Just return that state. That's the one we want. Otherwise, we'll go back to the top of the loop and we'll try again with the next parser. And the first one that succeeds, we'll return the state from. If, however, we're unable to get to the end of the loop, or we get to the end of the loop and we don't have a result, then we actually need to commit some kind of error. So let's update the parser error. And what we can say here is something like unable to match with any parser at index. Okay, so let's give this a try. Let's say we want to be able to, our parser is to just be able to match either digits or letters. That covers quite a lot of cases. So let's try this out. We'll throw in some digits here. And you can see we were able to parse them. We'll throw in some letters. And we're able to parse them. What you will notice is that if I add some digits and then some letters, that's of course only going to return the digits, because we're not saying, keep trying to get as many of these as possible. We're simply saying we would like to have either digits or letters. So why did I say that immutability was important? Well, let's go back to this line here and understand if our parser state was mutable. If, for instance, the string parser, instead of updating with a brand new parser state here, instead it overrode the index property of the parser state and simply returned that, then there would be no way for us to sort of recover easily from that. And that will often be the case in parser combinators, that you sort of want to be able to either run 2 or 3 different kinds of parsers and only take the output of one of them. You don't want to be sharing that state between each parser, so you actually make sure that it's immutable and you persist the state for every parsing result. There's one more parser I'd like to implement today, and that's the parser combinator many. What many does is it allows us to hand it a parser of some kind, and it will try to match that as many times as it can. So it's very useful in this instance where we want to match both the number in the beginning and the letters. So I'm going to copy choice. I'm going to rename it many. We don't take parsers here, we only take a single parser. We do all the normal things of propagating errors. We need to build a results array because we're going to have many things, so we need to put it into an array. And we should try to match this over and over again. So how will we go about this? Well, we take the parser. That parser is going to have a parser state transformation function. And to that, we'll pass our parser state. And this is going to give us a next state. And if the next state was not an error, then we're going to add the result to the queue. And then we need a way to jump back to the top. So we need to be in a loop here. So what I'm going to do is I'm going to use a while loop. We'll set a variable called done to false. And we'll say, while we're not done, if we were able to get a state out of this thing and the state wasn't an error, we're going to push the result and we're going to continue. If there was an error, then that's going to mean that we've got as much as we can out of this parser. Done is true. And of course, we need to persist this next state. So what I'm going to do is to create the mutable next state, initially set it to parser state. And here we'll copy that. It should be results. Okay, and then if we get to the end of the parsing result, what we want to do here is to return an update parser result. We want to add our next state, and we want to pass in the results array. You might be asking, why are we not checking for errors here? And the reason is, typically, the many combinator is implemented in such a way that it never fails. It always gets 0 or more results. And you can create a stricter version of many, and it's typically called many1, as if to say many or at least one. And all we have to do in that instance is to check the number of results we have. So if results dot length is less than or equal to 0, it could be less than. All we have to do is check that if the results length is equal to 0, we'll use our initial parser state, and we'll have the message many1 unable to match any parser. Unable to match any parser. Unable to match any input. So parser at index. Okay, so that gives us many and many1. Let's try that out. So we can just immediately wrap our choice in a many. Okay. Next state is not defined. 187. Of course, yeah. So we cannot shadow this variable here. Okay, let's try again. Another error. 172. That's in choice. And it's a similar thing. We're actually trying to use the next state variable, but it's not in scope here. So if we want to use next state, which in this case we don't want to, we should be using parser state here. Let's see if that is taking care of it. This error is true, but we have a result of the two captured states, which is interesting. We should definitely not have an error at this point, but we definitely do. And we got one from choice. Oh, okay, so this error is because many is running in the while loop, and we're overwriting next state, and then we're checking if next state is an error. And if it is an error, we say, okay, that's fine, we're done, and we skip out, but then we run an update parser result on that errored state, but we jam our results in. So that's why we see our results here, but we also see that we had an error from choice, because it already matched everything. So one of the parsers was returning unexpected end of input, or both of them were at this point. Choice is giving us this error, and we're just passing that down. So what we really should do is to say that this, for us, is a test state. And if the test state is not an error, then we push the result of the test state. If it is an error, then we're done. But what we can do here is after here we can set next state equal to our test state. And this should ensure that we always get the last valid state before we stopped. So if we try again, now we don't have any errors, but we have our two results. And so we could, just to tie it all together, we could use our map, we could take our results, and we could reverse the results array, for instance. Reverse is a mutable method, so probably best not to mess around with what we don't technically own. And here we've able to reverse using map. So I think we can leave it here for this episode. To recap, we built the primary mechanism for applying and modifying the structure of our parsing results using the map method, and a way of tailoring our errors to be more helpful to the end user with error map. We're able to highlight to us why immutable state is quite important in the parser combinator system, as well as being an extremely useful parser combinator. And finally, we implemented many and many one that allow us to capture many of the same kind of value in a row, without knowing exactly how many we should get. In the next episode, we're going to dive into how we can choose how we parse the next data based on the data we've already parsed. This is an extremely powerful parsing technique, and it's going to take us into some really interesting functional programming terrain. I really hope you've enjoyed this installment of the series. If you have any feedback, I'd love to hear about it in the comments or in the low-level JavaScript subreddit. Please consider subscribing if you want to see more of these videos. Thanks for watching, and I'll see you next time.